Hey everyone, welcome to our next session in the Agora Pods. Today with us is Nick Jenkins, and he is going to talk about onshore wind successfully lowering cost while building capacity. So, welcome. Thank you.
Thank you so much. As she said, I'm Nick Jenkins. I'm the Director of Energy Analytics and Economic Modeling at Radia. I've been spending the past 5 years thinking about how wind turbines will scale and wind turbine farms will look differently as we get bigger. And today I'll be talking about how GigaWind will transform the value of onshore wind. So the four main implications here are the following. So the big factor that we see first is the cost comes down. So as we see the turbines scale up, the number of turbines drastically reduces, and then we have fewer of them, which then reduces the capital costs. Not only the CapEx comes down, but also the operating costs reduce as well. The second one is we're also producing more power per turbine, and the consistency of that power is also improved. So our intermittency is actually reduced. The third one is that we are drastically able to scale out new viable acreage and markets in the US and globally. And then the fourth one is we're bringing back profitability to onshore wind. We've seen a lot of compressed returns in solar and wind over the past few years, and we think that with a lower cost basis, with the bigger turbines, we can now bring better profitability for our partners and investors in onshore wind. But not only is that the case for electricity, it's also the case for fuels, transmission, and any other C&I industrial uses. So over the past 2 decades, it's clear that turbine size is really the driver of economic performance of onshore wind. We're showing here the FAA tip height submittals over the past 2 decades. And keep in mind, the tip height scales with both the hub height and the blade length. So both of these things have grown consistently over the past 20 years. And you can see in the 2000s, we were at about 350 feet on average, pushing to 450 feet in the 2010s. And today we're at about 600 feet on average. Well, if we want to continue this trend, we're now up against transportation constraints that would allow us to get above the 650 feet mark and getting into 800 feet into the 2030s. Well, why is size so key in onshore wind? And it's because of the expression of the following power expression here we can see. As the turbine grows, we have 2 key parameters in the production equation that drive the bulk of the performance of the turbine. You can see as the power is a function of not only the air density, but also the swept area of the rotor. So as the blade length increases, pi r squared tells us that we have a square effect of the blade length going into the power production. Additionally, the mean wind speed, as it goes up, that actually has a cubic effect in the power production. So you can see that any additional blade length or hub height increase, which gives us additional wind speed, is a drastic implication in the amount of power you can produce per turbine. So over the past 2 decades, as we've seen the turbines scale up, we've seen a lot of cost reduction. And so you can see here that we've really drastically brought the cost down from about $100 per megawatt hour to about $30 today. And we see that for the next few years, the industry will likely find ways to kind of continue to reduce, continue to inch up, and get these bigger blades into new locations. But we see we've really realized most of the cost reductions. And it's not really until the Radia's Windrunner aircraft comes to market where we can provide a step change in the cost basis of onshore wind. So getting big is hard, and we're up against the constraints actively today. Even transporting a 70-meter blade to most locations is infeasible today due to the length. You can see we have chase vehicles, lead vehicles, sometimes years of planning just to get out of the road and find traffic problems or construction problems, and that's for a single blade. We'd often have dozens of permits that we have to have as we cross through different counties and states, and that's for just a single blade where usually wind farms you need sometimes hundreds of these blades transported at once. But not only is length a problem, also the width and height is getting to be a problem. As the turbine blades scale up, we're seeing that the root cord, or the root diameter, is getting too big to get under the overpasses in most of North America and most other countries. Additionally, the width. So the max cord length of the blade that really drives all the lift to turn the turbine also is so wide that it can take up between 2 and 4 lanes on the highway. So we're shutting down whole portions of highways to try to get a single blade pushed through to get delivered to the wind farm. So as most folks know by now, and you can see right behind you, Radia is bringing the Windrunner aircraft to market to be able to leapfrog these constraints and be able to deliver the blades directly to the wind farm. The beauty of the aircraft is not just that it can enable huge blades, it also sets the stage for growth of the industry. So we can transport 3 80-meter blades, which are just the industry's kind of largest blades we're starting to see today and really can't be delivered to most locations. We can transport 3 of them. So all that cost and fuel all gets divided by 3 when we actually consider it in the wind farm footprint. And then thinking about as we go up with the industry, we can then enable 2 95-meter blades, which are colossal, unprecedented size for onshore wind. And that will drive as high a nameplate capacity as 8 megawatts, currently unseen on onshore wind. Finally, getting into the 2030s, we expect to be able to utilize the capability to transport one single 100 to 4 and even 105-meter blade to the onshore wind farms, which can drive nameplate capacities as high as 10 megawatts. So we see this as really an analogous vehicle to the jackup vessels we saw offshore. About 10 years ago, the offshore wind industry was kind of up against the limits of trying to scale up in size, both in hub height and blade length. We had this new vehicle developed that enabled this industry to be able to go up to 200 plus meter rotor diameters that we're seeing today, where the Windrunner is really just the analogous vehicle that enables the onshore wind business to do the exact same thing. We're not trying to create any new nascent technology. This is just allowing the industry to continue to do the same thing it's been doing for the past 2 decades. So what we call this is GigaWind. We're introducing GigaWind, which is the largest blades today and the future of onshore wind, scaling up to above 100 meters in blade length. So when we take a standard wind turbine, typically about 70 meters today, it drives on average a 4 megawatt nacelle. We see a 16,000 square meter swept area. As we go to the GigaWind 104 meter blade driving a 10 megawatt nacelle, we more than double that swept area. So going back to that power equation, we are more than double our power output because of that swept area in the equation. What that does for us is it allows us to reduce the number of turbines drastically, sometimes even less than half the number of turbines, which means we're better utilizing the steel in the towers, the emissions, the roads, the electrical infrastructure, all reduces in scope. Additionally, we're producing more power and producing nameplate capacity more of the time, so it boosts our capacity factor. Those two, the CapEx reduction, the increase in the capacity factor, drives as much as a 35% lowering of levelized cost of energy for the wind farm. To kind of give a flavor for the economies of scale, we're showing here 3 platforms where today we're seeing the 73 meter blade. We can see we need about 223 turbines for a gigawatt of installed capacity, and we typically see about 39% capacity factor, and a levelized cost of energy of $28. As we scale up to that 80 meter blade, we're able to bring that down 15% to $24 and boost the capacity factor and reduce the number of turbines. Getting up to GigaWind's 100 plus meter blade capability, we can now bring the number of turbines down to 124, or almost half the number of turbines for a gigawatt installed. Also, we're getting capacity factors almost 50%. So for intermittent technology like this is unprecedented, huge implications for the market. Getting our levelized cost of energy down sub $20 or 35% reduction. Comparing to the rest of the market for clean energy technologies, you can see that GigaWind is by far making a huge implication in the cost basis of available power. So you can see here we have some clean technologies, nuclear, offshore wind. We also have some hydrocarbon technologies. But you can see that really solar PV and onshore wind, as they've scaled, have gotten to be very cheap. Now, the spread there is given by the difference in resource. We have windy regions, we have less windy regions, which gives way to the different LCOEs. We have good solar resources and poor solar resources, which gives way to that kind of spread. The cool thing about GigaWind is not only is it cheaper, but the high is much lower. The low is lower, but the high is much lower, so we have a less variability with respect to wind speed resource. And that's shown here as we're plotting here the levelized cost of energy versus the mean wind speed. So you can see up at 10 meters per second where the wind is very good, we have about a 15 to 20% advantage. But as you go to the left and you approach 5 to 6 meters per second, we're looking at a 35 to 40% advantage, or about a $40 per megawatt hour absolute advantage. So this has a huge implication on the energy transition, as most of the windy spots have been deployed already, and as we expand out from the wind belt, the wind resource is going to get worse. And so we see being able to provide competitive wind energy in more of the acreage is going to be a game changer. That being said, we've got about 125 gigawatts of wind power coming to the end of its life by 2030. And so we think repowering with GigaWind, where we'll have maybe a quarter of the number of turbines and doubling the capacity factor, will also be a game changer for those locations as well. So how does this look geographically? Most wind has been deployed in the wind belt, where about 7 meters per second or above is common. Well, because of the previous slide, where we can now deploy wind energy economically in low wind speeds, you can expand out drastically into the southwest, the southeast, all opens up to new markets where there's not any wind installed today. So this has huge implications on new markets for onshore wind, boosting the profitability of these projects. And so we think with the ability to transport large blades, we can make wind power economical across most of the US. Well, let's just take one example. Hyperscale data centers are going to need 28 gigawatts of clean firm power by 2030. This is just hyperscale. These are just the big tech firms are going to need clean firm power to drive AI demand. Well, because GigaWind can provide economical wind power across the US, this demand is not all in Arizona. It's not all in Wyoming where the resources are good. It's across the whole US. So we think using GigaWind is going to be a game changer here. With standard wind at a 40% capacity factor, you'd need about 70 gigawatts of total capacity to take care of that energy. That'd be about $100 billion in capital deployed. With GigaWind, because we have a higher capacity factor, we only need 60 gigawatts deployed. So we have less installed capacity. But also because our capital costs are lower, the total capital deployed also comes down dramatically. So you can see $70 billion of CapEx, 30% reduction in just for hyperscale data centers alone. Another way to look at that is over the lifetime costs of the power procurement. So you can see our PPA savings are dramatic. So you can see today you would spend about $3 billion over the lifetime of a PPA for these data centers, for a gigawatt of data center. Well, if you can deploy those 80 plus meter blades, that comes down $500 million to 2.5. Getting to GigaWind's 100 plus meter blade length capability, you can save $1 billion and bring that down below $2 billion for a gigawatt installed PPA. So data centers is not all. Also, the green fuels rise for decarbonizing hard-to-abate sectors. You can see here we're looking at the profitability of not only electricity, but for green fuels. So we take the typical IRR of 8%, and we boost that to 15% for standard power projects. But what's great about the higher capacity factor of GigaWind is that you better utilize all the downstream investments, such as electrolyzers. So we see electrolyzers are still very expensive today. With GigaWind being able to utilize them better, we actually push that return even higher than the 15% to 16%. So because you're adding more capital costs downstream, you're better utilizing it, we actually see those returns grow further and further into the value chain. The same is true if you want to get into ammonia or SAF or direct air capture or methanol. Anything you put downstream of a higher capacity factor technology will get better utilized and push your returns up. Thinking about the production profile of GigaWind versus other technologies, you can see if we're trying to get a high clean firm power, high availability renewable energy for a data center or some other C&I use, you can see that generally onshore wind provides sort of a base load. It's that dark green. It's more sporadic, but it produces more of the time. You also have solar, which comes on more dependently, but generally you'll see it come on in the morning, turn off at night, and then we overbuild that. We put also long duration storage. You can see the impact of GigaWind here just adds to the production level of onshore wind across the board. And what that does is it better complements solar and storage and better adds to your charge and discharge capacity of your batteries, being able to push up your availability to 95% in this case, is the example, for the same cost. If you take that same idea and you expand it out to the rest of the spectrum, we compare here two efficiency frontiers. We're plotting the levelized cost of energy versus the availability of the power. Each curve here has a combination of solar, wind, and storage. If we look at the dark curve, this is standard technology. We assume the first 25% is met with solar PV, so they're two are on top of each other. And then as you go up from there, you have wind, solar, and overbuild and storage, which grows that cost. Now the unique thing about GigaWind is GigaWind's actually cheaper than solar in most locations, so that curve trends downward. So to get to a higher capacity factor, it's actually cheaper. Then when you go up from there, the entire curve is dramatically changed because of that higher capacity factor and lower cost. It's just flatter as you go up. So you can say, all right, so for about $28 per megawatt hour, we could provide an additional 15 to 40% more production or better availability at that cost. Alternatively, at 80% coverage of clean power, we can provide about a 25 to 40% lower LCOE at that design point. So we think the implication of lower cost and more locations is going to drive the market to be much bigger and more profitable for the sector. As we see clean energies scale up in the next 2 decades, we expect nuclear, solar, and other clean renewables grow substantially. But if we compare onshore wind and where it's forecasted to take place, we can see that BNEF's projection of 10,000 gigawatts, we think we're only going to accentuate that or even grow that with gigawind being available. In conclusion, Radia's wind runner aircraft is going to have a dramatic impact to the onshore wind industry. We're just enabling the wind industry to do what it's been doing for 2 decades. Cheaply, cost-effectively grow the size of the wind turbines. And these large-scale turbines are the key to making wind energy a significant, economically profitable part of the energy mix in 2050. As these wind turbines scale up, the intermittency is reduced, the capacity factor is increased, wind farms become more sparse, and we do a better job at utilizing the materials in the investment. We open up new markets and geographies and lower wind speed regimes. And also the trade-off of cost and availability is dramatically changed for the better for all kinds of industrial and commercial uses like data centers, green fuels, extractives, manufacturing, and all the net zero ambitions that go with those. Thank you for your time, and I'll take any questions.
Thank you so much. So we are open for Q&A. Who wants to start?
So if I understood, the business model is to provide service for transporting these blades?
That's correct.
And so far, what's the consensus from the wind farm operators or wind farm designers? Do you have any dialogues going with them, and what's the feedback?
Yeah, it's a great question. So Radia is planning to be the sole owner and operator of the aircraft. We will work closely with the wind turbine OEMs to transport their technology to new locations and new wind farms. We're also, though, developing our own projects and working closely with other developers as well as developing our own projects, which will take advantage of this new technology. And working closely with the ecosystem, OEMs, developers, and Radia, bringing together the gigawind technology for onshore wind.
Next question.
I'm curious how you think about marketing the product, right? Because there's a couple of scenarios in which it's actually value destructive from a decarbonization perspective, right? Lower LCOE is not actually everywhere and always necessary to make projects bankable and competitive in the US, right? Yeah. And in fact, by increasing spacing to address wake effects of larger turbines, you're reducing energy output in order to get that lower LCOE, right? So how do you think about marketing this and inducing demand for these blades in places where it's materially additive to the expansion of turbines? I mean, this kind of speaks to your map of where in the US it opens up markets, right?
Yeah, so generally, I think, like I said, the people that are really interested in this technology are the people who have large investments like electrolyzers or data centers they need to power with clean, firm power, and they want to have a lower cost basis, right? So if they want a lower PPA price, you got to have that lower LCOE to go with it. From an on-the-ground standpoint, these farms are much more sparse, right? And so we actually have about half the number of turbines, which when you go talk to, say, the FAA, they really like that. It's better for the radar and the satellite operations to have fewer turbines. Now, these are bigger, but generally they're a lot more further apart. And so I'd say in terms of marketing, I think it's attractive to be able to have that higher value power where it's producing when other turbines are not. We're seeing that that's a really attractive, potentially more profitable aspect of these bigger turbines.
Any other questions? No? Okay, I think that's a wrap. Thank
Great.
you so much for
Thank
your
you.
presentation.